will be talking about basics first. We'll start with the basics of magnetochemistry and followed by the other units which will be dealing with the electronic spectra of the complexes. So before going into the details of the electronic spectra of complexes, we'll have an idea about the basic concepts of magnetochemistry. So to begin with, we'll first understand what is the pole strength of a magnet. So, in general, pole strength of a magnet is defined as the strength with which a magnet is able to attract a substance towards itself. So, here it is usually it is the unit pole. When we talk of a unit pole strength, we mean that it experiences a force of one dyne, and when the substance is placed at a 1 centimeter away from it. So, this is how, in general terms, we define a pole strength. Then coming to pole strength and lines of force. So when we have a magnet and it is the magnetic it is it the magnet, it has two poles, as we know. So according to the Gaussian law, when the magnetic flux through an enclosed surface, it is always equal to zero. That is what is called as the Gaussian law. And then coming to intensity of magnetization, this is represented as I. So the intensity, it is first we can say it is given as m by a, where m represents the pole strength and a represents the area of the unit area on which the magnet works. So in other words, we can say the intensity of magnetization is equal to magnetic moment by volume. So, in simpler terms, we have always defined magnetization in the intensity of magnetization as the magnetic moment per unit volume of a substance, and it is represented by I. Then there is a next term that is called as magnetic induction. So when we subject a body to a magnetic field which has a strength of H, and here H, it indicates the force that acts per unit area, then the total lines of force coming out of per unit area of the body is given as H plus delta H. So here we can write it as magnetic induction B is equal to H plus delta H, where delta H can be represented as 4 pi I, and here I represents the intensity of magnetization and which is magnetic moment by volume. So we can further write P, that is magnetic permeability. From the value of magnetic induction, we can write P, that is magnetic permeability, and it is given by B by H, which finally comes to the value of 1 plus 4 pi into I by H. So therefore, the magnetic permeability P can be defined as the ratio of the density of the lines of force within a body, and that in vacuum. And it is mathematically given as P is equal to 1 plus 4 pi I by H. Now there is also a very common term in magnetochemistry that is called as magnetic susceptibility. This magnetic susceptibility, the ratio that we have presented here in equation in 12.5, that is I by H. This is called as the here it is defined as the magnetic moment per unit volume per unit magnetic field, and it is known as kappa, that is magnetic susceptibility. It is this where kappa, it is characteristic of all compounds, it is different for different compounds. So from this we know that I is directly proportional to it. So here kappa is actually given as I by H. Here from this I by H is called as kappa. Then gram susceptibility, when we express here this chi, it is called as gram susceptibility, and the G here represents the gram, and this is given by kappa by rho. Or we can write it as chi b by rho, where this is the B here in this equation, it represents the volume magnetic susceptibility of the substance. Now also we can write chi m is equal to chi g into m. So chi here m, it represents the molecular mass of the substance, and that is why this is expressed in terms when it is multiplied with the gram susceptibility, then it results in chi m, and it is called as the molar susceptibility. Then coming to magnetic moment. Now in because there is a very this magnetic susceptibility, the term here that we are talking about, magnetic susceptibility, kappa or gram susceptibility, the kappa is actually very difficult to understand and to comprehend. So therefore, so instead, to remove these inconveniences, we take a more convenient property, and that is magnetic moment. So here the magnetic moment can be overall, this is when we look into the figure in 12.1, this shows the turning effect on magnetic dipole. So most cases we talk about magnetic moment, and that is given as mu. So this mu is the product of m into l. So this is the pole strength, and l is what is the here the length of the dipole I. So L, so this is mu is equal to ml. So most cases we'll talk about magnetic moment, that is mu, that is ml. So then coming to different the types of magnetic bodies. So here we will look into the types of the magnetic bodies. Now before going to that, we'll first consider this equation in 12.10, that is p is equal to 1 plus 4 pi kappa. So from this equation we arrive can two classes of magnetic bodies has been derived. That is, in the first case, when kappa is equal to 0 and b is equal to h, that is in vacuum p is equal to 1. So here we have a case where p is equal to 1. So when we look into figure 12.2a, in this figure it is for diamagnetic substance, and here negative kappa values, it gives the result that p is less than 1. So here is the one condition which shows that the p, that is magnetic permeability, is less than 1. And similarly in figure b, when we look into figure 12.2b, this is an example of a paramagnetic substance where the magnetic permeability is greater than 1, and we can see that more number of lines pass through it. So this is the two based on magnetic permeability, and based on this equation 12.10, two classes of magnetic bodies have been defined. One are the diamagnetism and another is the paramagnetism. Now when we to further understand this, let us look into figure 12.3. So this is in 12.3a, a particular case of paramagnetism has been shown. So here in figure 12.3a, this is a paramagnetic substance when there is no magnetic field. So we can see that the alignment is not proper here, but when in figure 12.3b we look here, the alignment, it is in a proper direction, so it aligns with that of the magnetic field. When the magnetic field is applied, then the poles, they have been aligned in respective ways. So the north pole of the micromagnets, they go attract towards the south pole of the applied magnetic field, and vice versa. So this happens in the case of paramagnetism. But whereas diamagnet, when we apply magnetic field to diamagnetic substances, the poles, they move away from the applied field and they get oriented at 90 degree to the applied magnetic field. So this is the difference between diamagnetic substances and paramagnetic substances. Now coming, there is also another classification of magnetic substances. So we have a term that is called as magnetically dilute substances and magnetically concentrated substances. Now when magnetically dilute substances indicate that there is no magnetic interaction between the nearby magnetic centers. So such substances where the magnets, the micromagnets, they are far from each other and there is no interaction inside them, so they are called as magnetically dilute. But in substances where secondary magnetic interaction occurs between the intermagnetic centers, they are called as magnetically concentrated. So with this, there arises two terms, that is ferromagnetic and antiferromagnetic. So now in figure 12.4b, this is particularly used for antiferromagnetic substances where the magnetic moment, it decreases due to the secondary interactions. But in figure 12.4a, we see it is a ferromagnetic substance where the secondary interactions within the magnet, it increases the magnetic moment. So this is also one another classification of magnetic bodies. So the magnetic susceptibility, that is the chi versus the temperature curve for different magnetic bodies, that has been shown in figure 12.5. So with this, in this figure we come across two very important points. One is these temperature, that is the Curie point Tc, and Néel temperature, that is we represent it as Tn. So these two temperatures are quite important in magnetochemistry. Now let us understand what happens when the chi, how it changes as a function of temperature. So when we look into figure 12.5 and we consider a diamagnetic substance, then the magnetic susceptibility chi, it does not change with temperature. But when we take a paramagnetic substance, the chi is inversely proportional to temperature. So now, since it is inversely proportional to temperature, there arises two different types of temperature. One is the Néel temperature. So Néel temperature is defined as the temperature above which an antiferromagnet it behaves like a paramagnet. And but below the Néel temperature, the magnetic susceptibility decreases with if you decrease the temperature. On the other hand, the Curie point, that is Tc, the Curie temperature is the temperature at which the ferromagnet it starts behaving like a paramagnet, but below this temperature the magnetic susceptibility it increases rapidly. So below Néel temperature, the chi it decreases with decreasing temperature, but for the Curie temperature below the Tc, the chi it increases rapidly. So here it has been shown in this, depicted in this figure, that if the two types of paramagnetic, ferromagnetic Néel point and Curie temperature has been shown here. Now in figure 12.6, here a simplified plot and the types of magnetic bodies and their ordering, that has been shown here. Now most of the coordination complexes that we come across, they are magnetically dilute in nature. That means the secondary interactions that occurring within the magnet centers, they are of dilute, they are like they are away from each other, and that is why they are dilute in nature. So in these complexes, the ligands may have the possibility for paramagnetic centers. So as a result of which, other atoms with separate donor atoms, they might not form any secondary magnetic interaction with these paramagnetic centers. However, we also have very magnetically concentrated substances, and then we will gradually later we will know on. So here in 12.6, the different spins and different arrangement of magnetic materials, they have been shown in a simplified form plot like ferromagnetic, ferrimagnetic, anti, para, and dia. So now starting with paramagnetism. So paramagnetism is first, to understand paramagnetism, we must understand that electrons have two types of motion. So first is their orbital motion, and second is the spinning about its own axis. So therefore, electron is associated with two types of motion, and as a result of this motion, two types of contributions they are made to the paramagnetism. So first is the orbital contribution, and other is the spin contribution. Now for the considering the orbital magnetic moment, let us look into figure 12.7. Here a single electron having a charge E and mass m, it moves through the nucleus with an angular velocity omega. So here it is shown in figure 12.7. Now the orbital angular magnetic moment, here it is given as the strength of the current into area of the orbit, so which gives us this value. The r hit represents the radius of the square of the orbit. So hence the orbital angular momentum has been found to of this value, that is represented in 12.13. So here the orbital angular momentum, that is mu l, it is represented as, in common terms, here it is represented as L into L plus 1 to the power half into beta. Now here beta is a constant and it is given as EH by 4 pi mc. That is the value of the beta that has been, that is, and it is a constant, and the value is this. So here when we these are in figure table point 1 types of magnetic bodies and their various temperature dependence, they are caused, here it has been shown. Then coming to spin magnetic moment, so when we putting the spin magnetic moment is given as mu s, as we represent the orbital magnetic moment as mu l, similarly spin magnetic moment is given as mu s, and the calculation, and it is given as the angular momentum into E by mc. Then substituting the respective values at respective places, we find the value of mu s to be 2s into s plus 1 to the power half into beta, where beta we have come across here and it indicates Eh by 4 by mc. Now here if we combine both the equation, that is mu L is equal to G into L plus 1 to the power half beta. Similarly, mu S can be given as G into S to the S into S plus 1 to the power half into beta. So here the G that is present in equation 12.16 and 17, it is called as the gyromagnetic ratio. That is, it is the ratio between the mu S correspond versus the spin angular momentum. That is, it is the ratio between the spin magnetic moment mu S by the spin angular momentum, which is given by S into S plus to the power 1 to the power half. So this is about paramagnetism. Now when we look into diamagnetism, we know that magnetic substances, they do not have any the magnetic poles. So as a result, when the magnetic field is applied, no interactions occur within the field, although some repulsions have been known, but no other attractions occur when magnetic field and external magnetic field is applied to a diamagnetic substance. So now if we look into here figure 12.7, here in this figure it is shown that when the magnet, it is an electron, it moves about the nucleus in an orbit. If it if it experiences external magnetic field of strength H, then and by the cone of the radius, here the radius of the cone, it is given as r1, and considering all the values, then the delta mu is given by this equation. So then finally putting substituting the Avogadro's value and all the, and we find this is the equation for a diatomic molecule, followed by finding the chi for a diamagnetic molecule, substituting all the values. Finally this equation, it has been obtained. So now, so in summary, for particularly for a diamagnetic susceptibility, we can say that it opposes the applied molecular magnetic field. So in order to show magnetism, the compound, it should have paired electrons, even though pairing of electrons is an inherent property of the substance. It is independent of H and T, although it remains as long as there is H. The magnitude of it, the of chi of diamagnetic substances, it increases as the radius of the orbit of the electron, it increases. So these are some of the general features of diamagnetic susceptibility. So now coming to paramagnetism. Now paramagnetism of any substance, it depends upon the population of the molecules in both the ground state and in the excited state. Hence, to calculate the paramagnetic property, the magnetic moment, it should be calculated by considering both the number of the population in the ground state and in excited state. So now first we have to understand what is thermal energy and magnetic property. So the ground state of a electron J of a multi-electron system with many J, we know it is decided by the Hund's rule. So with the magnetic property of a substance, we have to first consider it from the ground state. While calculation, it is always advisable that we start it from the ground state. So the multiplet width, that is the what we define as the gap between the ground state and the excited state. This gap is called as the multiplet width. When in the neighborhood of Kt, the thermal energy, then the excited states, they are significantly populated. So these three, let us summarize these three situations. So here in figure 12.9a, we see that the multiplet width is as large and it is almost comparable to that of Kt. Here we can see this is Kt, this distance, and the multiplet width, it is almost similar large as that of Kt. When we look into figure 12.9b, the multiplet width here, here if this is the Kt, then the multiplet width is much smaller as compared to Kt. But in figure C, the multiplet width here, it is comparable to Kt. However, the Landy interval rule is not satisfied, and in the figure 12.9, and it is in simple form. So here in this particular case, so we see the three different situations of the multiplet widths when they are compared to Kt. Now coming to calculation of magnetic moments for different multiplet widths. So when multiplet widths, they are as large as compared to kt. So here what happens is the L and S vectors that are here, the L vector is here and the S vector is here, they interact quite strongly so that J becomes a good quantum number. So here in figure 12.10, the coupling of LS vectors has been shown, and that the resulting magnetic moments have also been shown here. The direction of the motion of the negatively charged electron, it actually finally decides. So the movement of the electron finally decides the direction of the momentum. So here, so for example, here in equation 12.24, here we can find the value of G, that is given by G is equal to 1 plus J into J plus 1 plus S into L plus S plus 1 minus L by into L plus 1 by 2J into J plus 1. So this G, it can be put into equation 12.25 to finally get this value. Mu J is equal to J into beta into J into J plus 1 root over half to the power half. Similarly, the H by 2 pi is included in beta. So we know here the value of beta is substituted, and by substituting all these relations, from relation with the mu L and mu S, they can be derived easily. So for the orbital magnetic moment, S is equal to 0, so that J is equal to L and hence G is equal to 1. Therefore the mu L, it is given by this L into L plus 1 to the power half into beta. So when magnetic moment is spin only, so here L is equal to 0, so J is equal to S, hence G is equal to 2. Therefore the final expression for mu S, that is the magnetic moment due to spin only, it is given by the formula 2s into 2s plus 2 to the power half into beta. So now we know when we have a resultant spin quantum number s, this is given as the number of electrons into half, where half represents the spin. So here particularly the spin only, it is further, it is simplified and it is written as mu s is equal to n into n plus 2 to the power half into beta. So this is how we calculate mu L and mu J. So mu L for magnetic moment due to orbital contribution, and mu S is the spin only magnetic moment. So then coming to Curie equation. The Curie equation, it gives the relation between the molar susceptibility and the magnetic moment of the substance. The effective magnetic moment, that is mu J, it has to be found. So here as shown in figure 12.11, the J level, it splits into 2J plus 1 levels in the presence of a magnetic field. Since the magnetic fields, they become more ordered, it leads to a negative E. So here in figure 12.11, we see the splitting of G level on application of an external magnetic field, and some of the magnetic moments and energies, they have been shown here. So based on this, the Curie equation was derived, and the Curie equation is therefore found to be chi m is equal to n mu bar upon h. So here mu represents the effective nuclear charge. The bar on this, it represents the average effective nuclear charge. So therefore this mu is given as this much bm. So bm here, it is Bohr magneton and it is the unit for magnetic moment. So the then coming to Curie law and Curie-Weiss law, the magnetic susceptibility that was obtained here in 12.30, it is expressed in the form is chi m is equal to c by t, where c is the constant that has been obtained here, and it is called as the Curie constant, and it is characteristics of a particular substance. So here this equation 12.32, it is simplified, it was further simplified, and this form is now referred to as the Curie's law. So when we plot a graph of 1 by chi m versus t, it gives a straight line with then the slope is c that passes through the origin. So this is how Curie's, the plot is useful to calculate the chi m. So many cases they arise for paramagnetic substances where the plot of 1 by chi m versus t, that instead of passing through the origin, it comes with an intercept on the temperature axis. So this is given as the equation was further modified, and this was given as chi m is equal to c by t minus theta. And this modified Curie law is called as the Curie-Weiss law, and theta represents the intercept on the temperature axis, and it is called as the Weiss constant. So similarly, so in summary, Curie's law has been found to be true in cases where the ground state is more populated and is entirely responsible for the chi values, and the excited states are not possible by thermal excitation. And in second case, Curie law is particularly very true when the magnetic dipoles they are independent. So here is an example of some ideal Curie paramagnets, particularly chromalum, that is KCr SO4 whole 2.12 water. It is chromalum is a is a perfect example of a Curie paramagnet. So here in figure 12.13, a plot of Curie, that is 1 by chi m versus T for chromalum has been shown. So when we look into this, the here it is a example, the in the line it passes through the origin, and it is a perfect example that follows Curie law. Now, there are certain cases when Curie law is not obeyed, and these cases are if there is interaction between the magnetic dipoles, nearby magnetic dipoles, if the energy levels are populated and they differ when the temperature is changes. Now, when the and in the third case, so when the applied magnetic field it induces a temperature independent paramagnetism. So, in this following cases, the Weiss constant, that is theta, it comes into play, and here this equation in 12.33, that is the Curie-Weiss law, it comes into play. So when and for an antiferromagnet, the theta is negative, whereas for a ferromagnet, it is positive in nature. So therefore, the magnitude and the sign of theta, they can be obtained from this plot. Here is an example of a Curie-Weiss plot that has been shown. Now, when the multiplied width, it is quite small as compared to kt. So, if this is the case, then all the labels may be taken as to be populated. So, therefore, the mu it becomes L into L plus 1 plus 4s into s plus 1 to the power half into beta. So, here particularly in this case, the L and s factors they do not couple here. So, the magnetic moment from the spin and orbital effects are added, and ultimately this is given as mu of L plus S is equal to the mu j, which is L contribution of both the factors, that is L into L plus 1 plus 4s into s plus 1 to the power half into beta. Now when we have a third case that arising when the multiplet width it is comparable to that with kt. Now then here in this case, we have to consider the magnetic that is the chi m for each level along with the population of the j levels of each j level. So, and for this we need to consider the Avogadro's number. So, for this case, if we have to consider the nj plus 1, nj plus 2, then the chi will be given as nj gj square beta square j into j plus 1 by 3 kt. So, and particularly in this case, the Curie's law, it is not obeyed. So, here in the equation table point, this equation 12.37, it shows that magnetic moment here it is a quite complicated factor, or it and it depends on J and T, and that is why this is a very crucial calculation. Then coming to magnetic properties. So first, in order to understand the magnetic spectra and other properties, we need to understand the orbital magnetic moment. So for a free electron, here the value, here an example is given. The value of G, it is given by this 1 plus J into J plus 1 plus S into S plus 1 minus L into N plus 1 by 2J into J plus 1, and this value G changes when the chemical environment changes, that is when it no longer remains a free electron. This equation for 12.38 is particularly for a free electron, and this value changes with change in environment. So the first transition we'll first talk about the first transition metal series. We know they have higher magnetic moment value than that of spin only magnetic moment. So this is particularly this explained by the CFT. So in the complexes of the 3D series, the electrons they cannot go around the nucleus. So as a result, the quenching of the orbital magnetic moment it happens, and only the mu s value is considered. So the unpaired electrons in the first transition series they are located in 3D. So the electrons they have to rotate with the nucleus. They rotate around the nucleus you in their orbitals. So particularly in doing so, they should be degenerate in nature. However, we know that although the particularly they the dz square and dx square minus y square they are degenerating octahedral field, their shapes are such that one is not transformable into other by rotation. So the symmetry in the eg set they cannot generate any orbital magnetic moment. Hence this the dz square and dx square orbitals, that is the eg set in the octahedral field, they are called as a non-magnetic doublet. Here the non-magnetic is used because there is no magnetic moment that arises out of the orbital spinning. So but when the terms spin magnetic moment is still there, because the electrons they spin around their own axis, although they do not spin around the orbital, they spin around their own axis. That is why the mu s is still present here. Now, in the T2G set, there is dxy, dxz, and dyz orbitals that also obey certain conditions. So here, what happens here is the T2G set they will they it is depending on the type of the electronic configuration in the T2G set that finally decides whether it will generate a mu L, that is the orbital magnetic moment, or not. So these are some certain rules here in table 12.2. The expected orbital configuration in a high spin or a tetrahedral configuration with any of these they have been listed here in table. The higher the orbital configuration for various d electrons in octahedral and tetrahedral complexes has been shown. Now, from 12, this table, we can see that particularly for a nickel 2 complex or a tetrahedral cobalt 2 complex, they will have only spin only magnetic moment, but they actually show a magnetic moment which is much higher than mu s. Now, this could be because in the excited states of Ni2 plus, they particularly here in this case we have to consider their excited states, and in the excited states of Ni2 plus and cobalt 2 plus they carry the orbital contribution to the magnetic moment. So all the systems they have excited states, there is spin orbit coupling that is within the excited states that leading to some contribution to the mu value. So therefore, so comparing the mu effective value and the mu s value, we have this equation, that is mu effective is equal to mu due to spin only into 1 minus alpha into 10 dq. So here the E ground state has term where for the particularly for the E ground state alpha is equal to 2, and when we have A2 ground state then alpha is equal to 4. So when the ligand is strong and the crystal splitting is very large, so this orbital contribution is very less. So that is we can say depending on the arrangement of the electrons in the T2G cells, only then the mu effective can be calculated. So here for a low spin octahedral configuration, like for a low spin D5 complexes, it has on T2G to the power 5 configuration. So it will have the orbital configuration because it satisfies both the complexes, all the conditions. But when we talk of a D7 complex, it has T2G6 and EG1 configuration. Hence, it has no orbital contribution because one of the electron has now in the EG level and T2G is full. So this is how we calculate the mu effective. Here in table 12.3, the magnetic properties of the 3D transition series metals that has been listed along with their ground state term, the mu values, the mu j, mu l plus s, and the mu s, and along with the mu expected in Bohr magneton. In table 12.4, the octahedral transition metal complexes that have orbital magnetic moments have here they have been listed. Now here we can say that the all ground state all Mulliken states which show an orbital contribution to the magnetic moment are of T nature. If you look into this, these are all T nature. In 12.5, here it is octahedral complexes that do not have orbital magnetic moments. They have been shown here, and you can see the here into figure 12.5. So here we can say that all the ground Mulliken states which do not show orbital contribution, they are of either A or E. So as we know, so this we can say common that the ground Mulliken states which show an orbital contribution, they are of T nature, and the ground Mulliken states which do not show orbital contribution, they are either capital E or A in nature. Then coming to the lanthanoids. So here the lanthanoids, we know that the last electron it enters into the f orbital. So here the in table 12.6 the electronic configuration of lanthanoid elements have been listed. Now if we look into this table, the particularly the lanthanoid elements apart from f is equal to 14 and f is particularly here and here, where for F0 and F14 other all are paramagnetic in nature because of the fixing unpaired electron that is present here. If the starting and the ending of this series, all other elements within this series they are paramagnetic in nature. So so because of the presence of these unpaired electrons, paramagnetism occurs. The magnetic moment of only those ions, that is F0, F7, and F14, they agree with the spin only value. So here in all other cases, the magnetic moment they are higher than those are calculated. So in lanthanoid ions, the contribution of orbital motion is considered. It cannot be ignored here. So because the 4f orbitals they are better shielded from the 5f and 5p orbitals, then the 4f orbitals have unpaired electrons. So as a result, both the contributions they need to be added up, and that is why the magnetic moment values are much higher than those calculated only upon using the value of mu s. So here, as the spin orbit coupling constants is very high, the ls vector coupling it also effectively gives the j value. Here in table 12.7, the magnetic data on the ln3 plus ions it has been shown here. So the particularly we come across two cases which do not obey the mu j value. They are the samarium and europium. However, the magnetism of these two ions they can be considered by taking in line with promethium and terbium, and the j values for these four ions has been compiled together in figure 12.4, and here it is shown. In this case, the mu as is expected to be greater than than that is calculated, and that is based on the population of the ground state. So here, so the magnetic moment here it is given as j into j plus 1 to the power b half to the power bh. Here g is the Landau factor, and here it is given using this equation. So however, so then the values have been calculated and it matches with the experimental data. So in figure 12.5, the paramagnetic moments of the plot has been given here. The hump, it indicates here in the plot, when we observe a hump, it indicates the spin for the, here it indicates for the F0 electrons for the particularly the changes that we have observed here in case of europium and terbium. So coming to the actinoids they also have the lanthanoids that they resemble the magnetic properties with the lanthanoids, but the difference is that the 4f orbitals of the lanthanoid they are effectively shielded, whereas since the in actinoids the outermost electron it goes to the 5f orbitals, these 5f orbitals they are poorly shielded, and sometimes they also are also they remain bare. So here particularly, so here the magnetic phenomena it occurs to a greater extent in actinoid complexes. So one of the methods by which here this actinoid magnetic phenomena takes place is called as the super exchange. It is the way in which the complexes of lighter actinoids, they exchange their magnetic exchange. So here the RS coupling scheme, it is not valid, but the JJ coupling scheme, it is valid. So here in figure 12.8, it shows the electronic structure of actinoid elements. The experimental and theoretical mu j, that is the magnetic moments, have been calculated, and here it is shown. Then coming to the methods for for calculating chi m. So particularly, three commonly methods are used for the calculation of chi-m. One is the Goy method, the Faraday method, and the NMR method. So here in this Goy method, a magnetic sample, it is the arrangement here is shown in figure 12.16, and this is the standard Goy magnetic balance. Here HgCO it is taken as the standard for the measurement of Goe method, for the in the Goe method, to evaluate the magnetic moment of a particular compound. Here the Curie equation is used. Other calibrants, they have been used. However, this HgCO is mostly used because it is, however, because it has a low diamagnetic, because it has a good diamagnetic susceptibility, and it is comparable with others. Water has a very low diamagnetic susceptibility, and therefore it is not a good standard for measuring this. So figure in table 12.10, spin only magnetic moments, that is mu s and the chi m for some for unpaired electrons, has been shown here. Now with in this we have the derivation of Van Vleck equation. So to derive Van Vleck equation, two assumptions are made. That is the paramagnetic susceptibility, it is independent of the applied magnetic field H, and that the energy of the ith level in the atom or the ion, it is in a power series, that is wi, it is in a power series of wi0, wi1, wi2, and etc. So then comparing the considering the Zeeman coefficient arising due to the magnetic field, and overall combining all the equations, finally this equation, the finally for the Van Vleck equation, finally comes to this: chi m is equal to n sigma wi square kt minus 2 wi by the multiplicity of the level. So the importance of this equation is that the application is particularly is made in susceptibility measurements. Now the magnetic effects that arise from the electrons in a molecule, because the magnetic moment of an electron is about 10 to the power 8 times of that proton. So magnetic behavior, it is determined by measuring the magnetic polarization of a substance by a magnetic field, and for this there is a factor that is called as magnetic induction, which is described as B, and this B is given as H0 plus 4 pi m. This is the mathematical representation of magnetic induction. Then when we apply a magnetic field of strength H0 and m is the magnetization factor, the above equation, it is reduced to B by H0 is equal to 1 plus 4 pi chi V. Now here chi V is referred to as the magnetic susceptibility per unit volume. So then further simplifying this equation, we find that chi V by D is equal to chi G. So and from this we can again calculate chi M, is the molar susceptibility. So here diamagnetic substance, the diamagnetic susceptibility, it will be proportional to the number of electrons n and the sum of the squared values of the average orbitals, and therefore so for magnetic susceptibility measurement, the number of unpaired electrons needs to be first worked out for a compound or a complex under consideration. So in many complexes, it has been found that the moments and the temperature dependence, they are actually at a variance with their predicted values. So here what happens with the spin orbit coupling and the intermolecular effects, they need to be considered before for the actual calculation of the chi m. Now, spin orbit coupling for simple complexes of transition d metals, the spin only results they are obtained. So here, in addition to, so here, but in this section, certain equilibria has been That has been some examples, and other has been shown in the next section. So coming to magnetism in the metal complexes. So first is ferromagnetism and antiferromagnetism. Now, a ferromagnet, it is a body where the here ferromagnet in the magnetic centers, they are aligned parallel to each other, like here it is shown. But in an antiferromagnet, the magnetic centers, they are opposite to each other, like here it is represented. The phenomena of ferromagnetism is less common, but it has been more useful compared to antiferromagnetism. So now antiferromagnetism can be derived mostly for described in two types. One is due to intramolecular and other is due to intermolecular. So intramolecular antiferromagnetism, it occurs when the magnetic centers that interact are within the same molecule, that is, which they might be either polymeric, or mostly they can also be dimeric. For example, copper to acetate dimer. So here the this is an example of a intramolecular antiferromagnetism. So intermolecular antiferromagnetism, it implies the interaction with a secondary molecule. So particularly for metal halides like KMF3, where here M is a metal from the transition series, they have intermolecular antiferromagnetism. Now the mechanism of antiferromagnetic interaction. So here the magnetic moment, it might occur when metal interacts directly as a suitable metal overlap and super exchange takes place. So the super exchange, it takes place, it involves three atoms. So now we should know actually the influence of direct metal interaction on the mechanism of antiferromagnetic. So here in figure 13.1, so before we go, we should understand the metal interaction. So copper to acetate monohydrate, it actually exists in a dimer both in solution and solid states. The Cu distance here, it is given as this. So and this combination, they are separated by 2.64 angstrom. So the structure for this has been given in figure 13.1. So because the structure of this, that has been dimeric structure, that has been represented in figure 13.1a, a lateral overlap of the dx square minus y square orbitals, that is possible. So because of this lateral overlap that is represented in figure 13.b, a delta bond is generated. Now if we look into this figure, the total d orbital configuration can be given by this. Now in particularly, this we can see in the dx square minus y square, owing to the lateral overlap, one unpaired electron is present. So hence this gives rise to antiferromagnetism, that is due to metal interaction resulting in lateral overlap and formation of delta bond. Now for some complexes that have some subnormal magnetic moments, then there are other cases arises, like here the particularly if we look into the example here 13 point. Huh. Many complexes having metal ions where they are in low oxidation state, they exhibit the diamagnetic ground state. So in this complex, particularly Mn2CO10, it is a diamagnetic complex. Although Mn0 has a 3D system, this it is a 3D7 system. The Mn distance in this is 2.92 angstrom, and we know it is a D2sp3 hybridization. So the one of the six hybrid orbitals, it contains the seventh electron, while the other hybrid orbitals, they have the lone pairs. So the diamagnetism, it overlaps from the orbital that contains the single electron and the overlap from within them. So and here it has been shown. Then coming to super exchange. So the mechanism of super exchange, we know that this leads to formation of antiferromagnetic substance. Now here it leads to for the formation of both sigma overlap and pi overlap. So when we look into figure 13.3, it depicts sigma overlap and pi overlap for super exchange model. So here If we take into account the z-axis and assume that each metal ion has one unpaired electrons in its dz square orbital, then in this case, particularly in this case, and when we look into the pi overlap, we see the px orbital, it acts as the pi orbital, and then it overlaps with the dxz orbitals of the two metal ions. So here, for this such type of overlap, say the two this overlap, either the sigma overlap or the pi overlap, it causes the antiferromagnetism. Now here one of the examples of a dimeric copper skip base complexes, it has shown the table 13.5 has shows the predicted exchange interactions for different systems. And now coming to spin crossover and anomalous magnetic moments. So spin state equilibrium in octahedral symmetry and the crossover region. So we know the concept of pairing energy and from the CFSC that we studied yesterday. So here in figure 13.c we see 13.7 we see a high spin and low spin crossover region that has been represented here. So here we look if we look into the 3D8 configuration of a octahedral complex, this configuration it will not have the spin state equilibrium like Ni2 plus. So but when a 3D8 of nickel 2 plus, it has been found to have a spin state equilibrium. So hence we need to understand that complexes with tetrahedral geometry, they will not have spin state crossover region, and hence no spin state equilibrium is obtained for these cases. From figure 13.7, we can also say that the square pyramidal complexes for the D2 and D3 configurations, they will be high spin in nature. But those with D4 to D8, they may be low spin, because this happens because of the splitting of the dx square minus y square and the dz square orbitals. They have lesser energy as compared to that of P. Now valence bond and CFT interpretation of magnetic moment. So let us consider this hexamine cobalt 3 chloride. We know it is diamagnetic in nature and it is 3D66 system. So two cases here it arises due to one is sp3d2 hybridization, so which gives us four unpaired electrons and the mu is equal to 4.9 bm. This the for this molecule 3D6 system, there is also possibility of D2 sp3 hybridization. So here only one unpaired electron is present. So what happens here is this result in the case the spins are paired. So the compound here, particularly when we look into this, the compound it is an inner orbital complex. Here they are paired and here these are all unpaired. So according to CFT, if we look into this, these two types of arrangements are possible, and thus for D2 sp3 hybridization is possible. Then coming to anomalous magnetic moment. So there are various factors that give rise to anomalous magnetic moment within the complexes, and they are that if the two spin states are in equilibrium, if the unit cells have what sites that are magnetically non-equivalent, if there is possibility of solute-solvent interaction, if there is solute-solute interaction, and if there is configurational interaction, equilibrium. So these are the certain cases which gives rise to an anomalous magnetic moment inside the complexes. So here, if we first know, for considering when CFSE, we know that the in particularly in an octahedral field, the d orbitals they are divided into T2G and EG. Further, the tetragonal distortion of the octahedral geometry occurs, that is the John-Taylor distortion, and various types of, and they are further splitting of the orbitals that has been done, that we know. So now this anomalous magnetic moment, particularly it refers to those magnetic moments which does not match with the predicted values of mu s and mu l. So here these interactions from the interactions that arises from the interactions with neighboring molecules, they contribute to this anomalous magnetic moment. Now, for octahedral complexes, an example here it is shown the 382G octave ground state for nickel 2, it gets some orbital contribution from this term, and this is the result of spin orbit coupling. So, therefore, the delta value, that is the CFSE value, and the lambda, that decides the total magnetic moment. So, here the magnetic moment is given by this. So, this calculated mu effective is found to be this, and the corresponding mu s was found to be 2.83. So we see uh, these contributions from the next higher state term also influences the mu effective values in octahedral complexes. So similar cases has been shown with examples with iron, cobalt complexes. Now coming to tetrahedral complexes, particularly in tetrahedral complexes, relatively large contributions have been known from orbital angular momentums, and these are observed with Ni2 plus in tetrahedral field. So due to the contribution from other states, the expected contributions, they are influenced, and here some of the normal and anomalous mu effective for some complexes have been shown in figure 13.2. In square planar complexes, since they have no unpaired electrons and particularly they have zero moments, so small contributions to that they can be ignored. However, particularly for CO2 species having slightly large orbital contribution, they have been reported. So the normal and analogous magnetic moments for square planar complexes, here that has been shown in figure 13.2. So here some of the examples have been discussed for anomalous magnetic complexes. This is the case for cobalt complexes with certain examples for the mu effective, calculated mu effective values and the expected mu effective values. Now coming to applications of magnetic measurement for structural elucidation. Now this part, it deals with the use of the magnetic measurements in establishing the structure of various molecules. So if we look at the magnetically concentrated complexes, then the magnetic properties is very much dependent on the metal-metal distance. That is the magnitude of the metal-metal distance and the metal bridging, that is the metal atom, it is also very important. So and for this, XRD also plays an important role. So when we look into table 13.6 here, a variety of hydroxo-bridged copper dimers, the J changes from plus 172 to minus 509 as the copper-copper distance is increased. So the change in the ferromagnetic to antiferromagnetic exchange here takes place, and we can see the J values that has been listed in table 13.6. So here the impact of metal-metal distance is critical in establishing the J value and also in establishing the magnetic nature of the complex. Then the second factor that influences the magnetic property is the metal oxygen metal bridge angle, that is the delta MOM. This is very important. So in the hydroxo bridged copper 2 dimers that we have shown here, the magnitude of the J, we see it increases. The J, it increases as the bridge angle decreases. So when we look at into this angle, the bridge angle, it decreases, but the J value increases. And the crossover bridge and angle from there is a change from ferromagnetic to antiferromagnetic exchange. So here in table 13, figure 13.79, here the angle MOM versus J factor, they have been plotted, and the spectral properties here, the structural properties for these dimers, it has been shown in figure 13.7. So here we can see the square planar structure of the hydroxo bridged copper complex. It is in a ring fragment. So here it has been shown, but for particularly for one arrangement. Now if the arrangement has been changed, then we can see different overlaps and other configurations. Here these are the molecular orbital diagrams for CuO2 and Cr2O2 ring system, and some of the molecular orbital diagrams they have been given here. Then determination of the oxidation state of transition metal center. So during the formal oxidation state, number of the to determine the particular oxidation state of a transition metal center, chi m is plays an important role. So it is based on determining first how to number of unpaired electrons that are present in the central metal atom, that has to be determined. So after determining this, then we can calculate the oxidation state of the central metal atom. So for certain low spin CO2 plus complexes, here T2G6 Eg1, the mu effective is nearly 2.9 bm. But for high spin CO2 complexes that has the configuration T2G5 Eg2, the mu effective is nearly 4.9 bm. So the Bohr magnet also, looking at the mu effective value, we can actually predict the number of unpaired electrons that are present in the system. So this chi m has also been used for the determination of electronic configuration of the transition metal center. Like for complexes, when the when the central atom is transition metal, the high spin and low spin configurations, they have difference in their energy and their thermal energy. Like for example, we have FeFe6 FeF6 3 minus, this is a high spin complex, and a low spin complex like FeCN6 3 minus. So here the energy varies, and the thermal energy, it also varies over a wide range of temperature. So first we need to, so particularly in this case, the high spin and low spin configurations, they have an energy difference which is comparable to their energy, to their thermal energy. So we can find out during this sort of spin equilibria how there is change in the number of unpaired electrons, looking at their chi m values, that is their magnetic susceptibility values. Like for example, nickel 2 plus is D8. It has some diamagnetic square planar complexes which converts into paramagnetic tetrahedral or octahedral complexes having two unpaired electrons. So this, the change that we can observe here, it will indicate the number of the unpaired electrons, and we can find out the electronic configuration on the metal center. Then, using the value of chi, we can determine the stoichiometry of various transition metal complexes. So here, to find out the stoichiochemics, the stereochemical arrangements, we have to first, the particularly the value of chi, it has been determined this, and there are two methods to find out the stereochemistry of the complex from chi values. The first one is, it depends on identifying the number of the unpaired electrons, and the second one, it requires the finding out the exact amount of the mu l, that is orbital magnetic moment. So for this, how we can find stereochemistry from unpaired electrons? The first step here, it is that we need to exactly find out the total number of unpaired electrons. Now particularly when we have D0 and D10, they are they are symmetrical in nature because they have full configurations. So linear, triangular, for tetrahedral, TBP, octahedral, and pentagonal bipyramidal, they are for 2, 3, 4, 5, 6, and 7 coordination number that we all know. So when the symmetry of the cloud, it gets lower, then the geometry also, it gets changed. So we have learned about this tetragonal geometry. So the expected stereochemistry and the transition metals of the, using counting the number of unpaired d electrons, can be done from this table. Suppose the number of d electrons here, it is d0, so it is symmetrical in nature, and therefore they cannot be predicted. Now when the in and weak field, if it is, that is d1, so it indicates T2G1. So it should be, so here it is slightly the distorted octahedron. Similarly, so we can look into this table and predict the various, the stereochemistries of the different transition metal complexes. So the electronic configuration made from D1 to D9, they are different, and distortion is expected. Now coming to determination of the stereochemistry from orbital magnetism. So here, to understand this, let us consider a few examples. So, the mu spin only, it should be 3.88 in the spin free complexes of CO2. However, the CO2 tetrahedral complexes, they do not have any orbital degeneracy, and if the total the spin orbital coupling is ignored, its mu effective is expected to be comparable to mu SO. But when experiments have been done, the effective mu magnetic moment, it has been found to be 4.5. So therefore, by even so particularly for D5 complexes, here the large value of orbital magnetic moment, it leads and they're found to be 5.1. So therefore, if we can differentiate between the tetrahedral and octahedral complexes, and we know the nature of orbit magnetic moment, then we can actually predict their stereochemistry. So these are certain in table 3.13.9 stereochemical arrangements in spin free and spin paired complexes. That has been listed here. Then coming to unit 14, that is electronic spectra of transition metal complexes. So coming to, before starting with the electronic spectra, we should know about, first know about the four quantum numbers, that is the principal, orbital, magnetic and spin quantum number. The orbital, it can have L values from 0 to n minus 1, and the magnetic quantum number, it can have minus L to plus L. So and the spin quantum number, it has two values corresponding to the spin of the electrons, that is plus half and minus half. So here the orbital quantum number here L, it is given as L into L plus 1 to the power half into h by 2 pi, and S is given as this. Then the orientation of L and S vectors with respect to the magnetic field, they are quantized. So here in the figure 14.1, the possible orientations of the orbital vectors, particularly for L is equal to 2, they are shown. Now before going into the details of electronic spectra, let us understand what is JJ coupling and Russell-Saunders coupling. This RS coupling, it is applied to particularly to the 3D series, the lanthanoids, and not very heavy metals. So here the spin vectors, that is the S of different electrons, they couple together and they finally form the resultant, that is given by capital S, and all the L contributions, they come together and form the final contribution, that is the L, and finally the S and L vectors, they combine to form the J vector. So this is the, in figure 14.2, here the coupling of L vectors, and the 14.3, it shows the coupling of LS vectors to produce J. So in a heavy atom, the coupling of the L and S vectors, they are forced by the higher nuclear charge, and thus they resulting in the J vector. This small j, it is called, it is given as J into J plus 1 to the power half into h by 2 pi. It is also the corresponding quantum number J. So we can find J vector from the small j vectors by this equation. So this is what we call it as JJ coupling. Then coming to coupling of orbital angular momentum. So first an example here, it is given for p square configuration. The angular momentum, we know it is quantized, that is it comes in packets of magnitude of h by 2 pi. So here for a p electron, we know the azimuthal quantum, the L, that is 1, and the orbital angular moment here it is given by 1 into h by 2 pi. So the different resultant of L terms of P2 configuration here it has been shown. So the vector diagrams that has been represented here in figure 14.4, they actually, the vector diagrams, they depict the possible interactions between the L values of the P2 configuration, means 2p electrons. Now, since angular momentum here is, it is, we know it is quantized, so configurations that provide only a whole number of h by 2 pi, they are allowed. The configurations where h by 2 pi is fractional, it is not allowed. So as a result, the spectroscopic terms d, p, and s, they have only three different states. The vectors, the L for the p state, it must be an angle to one another, and here the case has been shown, different resultant cases have been shown. Now similarly, considering for a p3 configuration, so for a p3, so 1f, 2d and 3p states and 1s states are produced as a result of coupling. So these are the result of resultant L terms for P3 configuration. Then this is for the P. Now coming to a simple case of D2 configuration. So a similar pattern, when we can say, we look into the L value of D. For a D orbital, the L is equal to 2. So the coupling of the L values for D electrons, it also follows similar pattern, except here for that the d electron L is equal to 2. So what we see, the arrows here in comparison to this, they occupy a double. They are double in their length. So these are the resultant for L terms for D2 configuration, and further such configurations can be done for other D system. Then comes the coupling of spin angular momentum. This, the spin quantum number that we call it as M. It is of an individual electron, it is plus half or minus half. So when the two more electrons they are present in a subshell, the resultant, the magnetic fields, they interact, or what we call it as the addition or the coupling, to form that capital S is equal to form, this is the coupling which gives, and it is indicated by capital S. So for a P2 or D2 case, we can find that the resulting capital S, its spin quantum number, it has a value of 0 or 1, and we can use the arrows to represent the quantized energy. Here figure point 7, it has been shown the resultant S values for P2 or D2 configuration. Similarly, here S has a particularly, here we can see it has either plus half or minus half. Similarly, when we consider a P3 or a D3 case, so this is for a P3. So the resultant here, it is either 1.5, or here this is the resultant, here it is 0.5. So likewise other cases can be drawn. Now the considering both the spin orbit coupling. So here the resultant capital S, it is the spin quantum number. It indicates the overall, the individual spins that are present, and similarly the consequent quantum number capital L, it indicates the individual orbital angular momentum, that is small l. So small l is represents the individual angular momentum, and small s, it represents the individual spin quantum number, and the capital S indicates the summation of the factors. So the vector combination of L and S, they result in a new quantum number that is called as J, and this J is known as the total angular momentum quantum number. So when the magnetic fields they interact with, like L plus J, when the magnetic field, orbital magnetic field and the magnetic field, they interact with each other, it forms J, and this is known as the LS coupling or the Rochelle-Sanders coupling, that is the RS coupling. So now we already know that when we have a P2 arrangement, this will look into the case of a P2 arrangement. For a P2 arrangement, capital N is equal to 2, 1 and 0, and the resultant spin quantum number, that is S, and S is equal to 1 and 0 are obtained. Here we have seen S is equal to 0 and S is equal to 1. These are obtained. So now these combinations, they couple again together, the L and S, they couple together to form the angular quantum number, that is J. Here it is shown in figure 14.9, the various possibilities of the term symbols, that of the combination, and along with their term symbols, that has been represented in figure 14.9. So the 3p and 1d states, if we look into this, it account for 9 plus 5, that is 14 combination, and the remaining corresponds to this. So here this is how we the linear combination should be taken, and other can be drawn. Other, this is for particularly for P2, and other they can be drawn similarly. Then comes the Raka parameters. The Raka parameters, they give a summary of the effects of the interelectronic repulsions of the energies that that stops from a single configuration. So these are expressed as B and C. These are linear combinations of certain Coulomb interactions and exchange interactions that are related with the uncomplexed ion. So the detailed configure here Raka parameters have been discussed in the Tanabe-Sugano diagrams. The correlation spectroscopic terms. So first, let us take an example of a metal with a 3D2 configuration. So it has here in this case the 1s2, the 1s, 2s, 2p, 3s, 3p, these levels are all filled. So the orientations, particularly the of the 6 electrons in the 3p level, here they are represented. Here we can write it like this. So for we know for a p level, the azimuthal quantum number here it is plus 1, 0 and minus 1. So and the correspondingly for each electron the spin quantum numbers have been given. So here when we look this result, looking at this result, we find sigma ms is equal to 0. That is the magnetic spin momentum quantum number, and s it must be 0. So even again we look into the resultant magnetic orbital quantum number, that is capital L, it must be 0. So all these, they will not, these atoms or ions, they, with their, since they contain field shells, they will not be able to show paramagnetism. So therefore, the ground state of the 3D electron configuration, it must come from 2D electrons. Hence, thus, in particularly while writing this configuration, we have to follow the following Hund's rule. That is, the ground state is characterized by the highest spin multiplicity, that is the maximum possible number of unpaired electron spins. Second rule, the ground state is characterized by the highest possible orbital multiplicity, that is the highest value of resultant orbital quantum number. And the third rule is that when we have a half filled or less than half filled shell, the ground state has the value of the J, where more than a, and for more than a half filled, the ground state has the highest value of J value. So here 2s plus 1, it is called as the spin multiplicity, and this gives us the, if 2s plus 1 is equal to 3, then there are 2s is equal to 1 unpaired electrons. So the following J values can be this. The modulus is given because neither S nor L here, they can be negative in nature. So this is how Russell-Saunders coupling has been used. Figure 14.10, the splitting of carbon in ground state has been shown for particular using the Russell-Saunders coupling scheme. So here these are some of the examples with which we can the RS coupling scheme it has been used. And table 14.1, it shows the ground state term symbols for 3D configurations. Then coming to microstates and derivation of RS terms. So first, microstate means it is an electronic configuration that has particular ms and ml values. So if we see a particular combination that has ms and allowed, where both ms and ml values are allowed, they are called as a microstate. Like for example, if we take a simple or p2 configuration, so now we know, but for this P2 configuration, two states are possible. That is ML, we know it is plus 1, 0 and minus 1. And the MS, it is usually given by plus half and minus half. So this is for a P2 configuration. Then when we, for microstate, that indicates 1 plus and 1 minus. It indicates that one of the two electrons has ML is equal to plus 1 and MS is equal to plus half, and the other has ml is equal to plus 1 and ms is equal to plus half. So this is the indication of this microstate. So a p configuration, it can, so thus for this particularly p configuration, 36 types of arrangements have been possible. However, among these 36 types of arrangements, 6 of them, they do not obey the Pauli's exclusion principle. So after discarding the 6, The remaining 30 arrangements, only half make sense because the electrons are same. We have not separated the electrons. So for example, 1 plus and 1 minus and 1 minus and 1 plus, they can are indistinguishable. So here only 15 such microstates are possible for P2, and thus it is indicated here. The all these combination of these states, it show that how for a particular P2 configuration only 15 microstates are known. So here we can see. Now similarly, the P2 configuration, it has three Russell Saunders scheme. So here the which are 1D, 3P and 1S. Now from this we have to know which is the ground state. So according to Hund's rule, so the 3P, it has to be the turn symbol. So now we can again calculate the multiplicity. So accordingly the multiplicity can be calculated from this formula, and we get 1D 5 microstates. Particularly for 1D it has 5 microstates, for 3P it has 9 microstates, and for 1S it has 1 microstate. So therefore a total of 15 microstates can be identified for P2. Now similar example has been given with D2 configuration. So putting all the substituting the values, 45 possible distinct microstates for D2 configuration has been identified, and they have been listed here in figure table 14.3. Now the various RS terms for the PNN and DN configurations in table have been listed in table 14.4. Here it has been shown. Now the ground state term, we particularly, it has, they are identified by putting a asterisk in the superscript, that it has been shown here in table 14.4. So while determining the term symbols, a few points need to be considered. The electrons, it should be unpaired as much as possible, and they always occupy the different ground states of lower energy. The spin multiplicity, it must be maximum to be stable. The angular momentum, that is, or the capital L, it should be the highest for the ground state, and the capital L and S, they should couple to give the J, that is the total angular momentum quantum number. So if the subshell is more than half filled, then the smallest J value is more stable, and if the subcell is half less than half filled, then the highest J value is more stable. So here certain examples have been shown. This is the correlation diagram for an ion in octahedral field. In table 14.5, the splitting of DN terms in an octahedral field, here it is shown, and the terms have been shown here. The splitting of these terms in an octahedral field has been shown here. In figure 14.12, the splitting of an octahedral field of the ground state terms that arising from D1 and D2 electronic configurations, here it has been shown here. Then coming to Orgel diagrams and Tanabe-Sugano diagrams for transition metal complexes. So these diagrams, particularly Orgel and Tanabe-Sugano diagrams, they have been quite helpful in determining the, particularly for octahedral and tetrahedral symmetries of complexes. So before understanding these diagrams, we need to understand the selection rules that govern the electronic transition that occurs between the metals and the ligands. So for this, the selection rules, they deal with the forbidden transitions and the allowed transitions. So here in figure 14.3, some correlation diagrams have been shown. So first we'll start with the first selection rule. This is called as the Lapote rule. So this statement states that only those transitions allowed are allowed which occurs with a change of parity. That is, G to U is allowed, U to G is allowed, but G to G that and Girard to Girard is not allowed, and ungirard to ungirard is not allowed. So this means that D to P, that is transition from D orbital to P orbital, S orbital to P orbital are allowed, but DD transition, S to DD transition, they are not allowed. So now coming to here, if DD transitions that we have come across in octahedral complexes, they are they are not allowed as per Lapote forbidden rule. But we know that these transitions, as we have studied in complexes like TiH2O whole 3 plus, which show electronic spectra due to DD transition, then these DD transitions, although they are Lapote forbidden, they do occur in very low intensity. That is why we see the color of the complex. Now, vibronic transition, that is, vibronic means the term vibronic is the combination of vibrational and electronic. The vibrational part, it corresponds to the IR spectra, and electronic transition, that is mostly in the UV region, they result in instantaneous unsymmetrical conformation and they give rise to the observed spectra in these cases. Now, but the spectrum, the molar absorptivity, that is the epsilon, for the octahedral complexes where DD transitions are happen, they are very low in nature, and that is why although they occur with very low intensity, the DD transitions, they are still imparted with a certain color. Now, when we look at tetrahedral complexes which have no center of symmetry, and that is why they have no G or EU designation that we know. But the E and T2 orbitals, they have been derived from the orbitals which have some symmetrical properties. So that is why the non-bonding E orbitals, they are the metal D orbitals, and their G character is still present in the complex. So therefore, but the T2 orbital, they are formed from mixing of the D atomic D orbitals. So here what happens, considering the tetrahedral complexes, if we look into the spectra of tetrahedral complexes, the epsilon, that is the molar coefficient, it is much more larger than those obtained in octahedral complex. Then first is the Lapote rule, and the second comes the spin selection rule. So according to the spin selection rule, the transitions may occur between the energy states when only when delta S is not equal to 0. That is, so delta S, in order to be allowed, so for a transition to be allowed, it must involve no change in the spin state. So what happens here is, there are so among these complexes where delta S is not equal to 0, it is spin forbidden. So for a delta S, for a transition to be allowed, delta S has to be 0. So a D2 complex, it should give rise to an electronic spectra consisting of three absorption fields. So when we increase the field strength, then the separation between the triplet and the excited state, it's become larger. That is why when we consider the for particularly the color and the color of the corresponding complex, it shifts. So here when we see here, it is for 3T1G to 3T2G, from we see this, the epsilon is 17,200, and here we see it is 25,700. So this is, since the as a because of the change in the epsilon values, the color are also changed because the band is shifted to different parts of the UV region. Now here, this D5 correlation diagram, it is for particularly here, it is shown that we have shown why it is much different, because the ground state 6A1G is the only state which has a multiplicity of 6. Now, this makes the transitions very weak because they become both Lapote forbidden and spin forbidden. And this is what makes all the dilute solutions of Mn2 color less in nature. So here, when we take higher concentration of Mn2 plus, we see a faint pink color, and this particularly for D5, we see that it is the only state where which has a multiplicity of 6, And since both are Laporte forbidden and spin forbidden, these the spectra of particularly Mn plus 2 complexes, the complexes, they are not colored in nature, they appear colorless. Now it has also been observed that for complexes which show spin orbit coupling, the spin selection rule is not somehow followed. So this is one of the reasons that the complexes of the heavier transition metals, they have certain transitions that are not been that do not follow the spin forbidden rule. So if you look into figure 4.6, here we see that the D1, D4, D6 and D9 configurations, they only show very they show very weak field ligand, they have an absorption value which is delta O. Whereas particularly in this situation, the D2, D3, D7, D8, which have spin allowed transitions, the energy difference is also delta zero. So we must know here that the D5 octahedral complexes, they cannot have any spin allowed transitions. So here particularly, here they are none because they cannot have any spin allowed transition. Then coming to Orgel diagram, these are one of the most important diagrams and that has been used for understanding a complex. The Orgel diagrams, they predict the number of the spin allowed absorption bands in UV visible spectroscopy. So when we look into figure 14.15, this is the Orgel diagram for CO2 plus in a tetrahedral field, and here it is in an octahedral field. So here they have been represented. Now a complex of CO2 plus, it can shows a spectrum here with three types of absorption. So here in figure 14.6, this is an Orgel diagram where high spin octahedral or tetrahedral complex, particularly for D2 to D8, they have been shown. Now apart from their intensities, so the interpretation of the spectra, we actually, for to look into the interpretation of the spectra, we have to look into the widths of the bands that are observed here. Now since we were talking about TiH2 whole 6 3 plus, we know it has a very broad absorption single band because firstly there is a DD transition occurring here, and as such they are very weak transitions. So and it is has a very the because the of this particular TiH2O63 plus, the UV spectrum, it appears very broad in nature. Now, when we look into here, figure 14.17, so here this is a solution of Mn2 plus and it shows sharp peaks. So here the changes in CFSE in the octahedral field, it does not influence the transition that occurs between the ground state and the excited states. So also we can see that is why the here particularly we see sharp peaks, and this might be also due to the John Taylor effect and destruction of the symmetry. And then diagrams that are produced by Tanabe Sugano, they are frequently used to illustrate the variation of term energies with field strength in order to properly address the problem of spectral interpretation. Here in this is figure 14.18. It is a simplified D6 Tanabe Sugano diagram. So here is a very simplified approach. The abscissa represents the ground state, and here if we look into the x-axis, it represents the ground state, and the arrow spins here, they have been represented in the uh, allowed. The arrows here particularly, they represent the spin allowed transition. Now interelectronic repulsion, here it is expressed in terms of the Rache parameters B and C. So this is how we represent the simplified Tanabe Sugano diagram. The free ion values of the parameters for different gaseous transition metals, it has been shown here. Now, in figure 14.9, the spectrum for COEN3 plus and CO oxalato 3 minus, it has been shown. So to particularly to calculate the delta and B, that is the Raka parameter, we have to fit this spectrum into its to Tanabe Sugano diagram. So then after this we have to find the Nephaloxic effect ratio, that is beta is equal to B dash by B, and this equation followed by from the Tanabe Sunabo diagram we can find the value of delta B, and then we can calculate the energy. So here one example here has been shown for the low spin complex COEN3, whose spectrum here it is shown, and the bands that has been obtained are given here. Now first we need to take the ratio, and here we find out from the B dash by B. So this is equal to always the this is the first the ratio we find out the beta, then it is fitted into the TS diagram here as it is shown, and with the help of a different ratio. So here we can, and then calculating that we find that the value is found to be 38. So the main part that needs to be done here is the splitting of the orbitals, and then the here from the diagram we have to calculate the different energies. So some of the TS diagram for D2, D3, D4 it has been shown here, and using these diagrams we can calculate the, first we'll calculate the beta value, and then we will calculate the energy values. And then coming to the last part of today's class, this is charge transfer spectra and assignment of configuration. So first coming to origin of charge transfer spectra. So charge transfer spectra, these particularly these are the various types of expected and unexpected transitions that have been we know. So whenever there are change, there is a charge transfer transition. There is possibility, two possibility. One is the LMCT, that is the ligand to metal charge transfer, and other is the metal to ligand charge transfer. So that we will come across, this is the various types of transitions, like the spin forbidden, which is the DD. So the epsilon max, that is the molar absorptivity, here it is less than 1. Then the Laporte forbidden, which we call it as the DD transition, and particularly here we can see the TiH2O whole 6, here it is 1 to 10, the epsilon is very less, and the transitions which are fully allowed, the epsilon is very more, and that is why we obtain a very intense coloration and sharp peak. This is the for some of the transitions that have been listed. And coming to vibronic coupling, so as the word vibronic, it combines two words, that is vibrational and electronic. So electronic transition, usually it means the UV visible region, and the vibrational transition, it usually means the IR region. So combination of this, it gives to the possibility of the vibronic coupling and the corresponding spectra. So now we know that the DD transition in octahedral complexes, they are Laporte forbidden because the symmetry is same, and we know same symmetry, for that it is they are forbidden in nature. So but we have observed some, like in the TiH2O whole 3 plus, there a spectrum has been observed, and that has been explained by vibronic coupling. So for the vibronic coupling to be allowed, the transition moment, it has to be non-zero. Now, but for this complex, the DT transition, it is observed through vibronic coupling. So here in this situation, the angular momentum, it will cancel out the angular momentum of the electronic state. So as a result, the transition takes place without any change in the rotational state. So this is how the vibronic coupling takes place. So now coming to LMCT, that is ligand to metal charge transfer transition. So whenever LMCT takes place, the electrons are transferred. As the name implies, the electrons, they are transferred from the low-lying molecular orbital that are principally present in the ligands to the those that are metal based. Now this transition from ligand to metal, so this transition and post transition metals, they are much important, because such transfer, it would be favored, and it has quite high energy. So it is these ligands, they which favor this type would be non-metals having low electron affinity. So in LMCT, intense bands, they are observed, And these, since these are Lapote allowed transitions, so the origin of LMCT transitions, here it has been shown in figure 15.1. Although they have a very short half life in their excited state, but the transitions are very intense in nature. The electrons are first excited from the low lying pi orbitals of the ligands to the T2 Eg or the Eg of the metal atoms, then which leads to the charge transfer. So here the UV visible spectrum of cobalt 2 plus, here it has been shown, and here we do see a very intense spectra. So in figure 15.2, the spectra of this ion is shown. So, and then here we must be knowing that halides, the depending on the type of the ligands that have been complexed with the metal, then the epsilon value, that is the molar absorption coefficient, can vary, and the intensity of the coloration can also change. Now here the comparison and ease of certain, so reduction of metal ions that has a greater intensity on their absorption has been listed. So MLCT is metal to ligand charge transfer spectrum. So in this spectrum, the metal orbitals, they supply their electrons, they are in their low lying electrons, and they supply to the empty pi star orbitals of the ligand. So examples of this complex this has been given. So here in all these cases, the pi star empty orbital they present on the ligand, they accept the electrons with the introduction of light and absorption process. So here tris bipyridine ruthenium chloride, that is RuBpY whole 3 Cl2, it is a very common MLCT induced MLCT associated transition, and here this is the structure and this is the UV visible spectrum. So here is the absorption spectrum and it is mostly due to MLCT, and here it is the emission spectrum, here it has also been shown. So particularly here the metal, it undergoes oxidation as a result of this charge transfer within the reduction of the metal. So the ligands which have a low lying vacant pi star orbital, that is particularly pyridine, they gets reduced in this process, and as a result this type of conditions occur. So here the origin of MLCT charge transfer bands has been shown here. Now coming to the effect of solvent polarity on CT spectrum. Now we know solvent has a great role in charge transfer spectra, as it has its capacity to solvent an effect on the transition. It influences on the transition energy of the transition that occurs. So if we use a highly polar solvent, then the wavelength shifts to the lower value or higher frequency. Now, polar solvent molecules, they align their dipole moments perpendicular. So the nephelauxetic series, it is given by here, it is represented here. So the ion, particularly when we look into this ion, fluoride ion, it has a small reduction in B. While if we look into iodide, it has a large reduction of B. Now this series, it is not similar to that of spectrochemical series, which gives an indication of the CFSE values. Then coming to spectroscopic methods of assignment of absolute configuration in optically active metal chelates and their stereochemical information. So here we'll be dealing with the assignment of absolute configuration in optically active metals, and further we will talk about their stereochemical information. So as we know that the lowest dd transition is always, particularly we'll consider a hexamine cobalt 3 complex, and it is T11G to A11G. So for this complex, for this COEN3, and we observe a visible spectrum. So there are particularly two phenomena that is associated with DD transitions. One is called as the ORD, that is optical rotatory dispersion, and another is called as the CD, that is circular dichroism. So these two are actually very important, and for to know the absolute configuration of a complex. But however, it is just on the basis of the movement of the plane polarized light, we cannot know the absolute configuration of any complex. So before that, first we have to know the chirality, and then we have to correlate the first. There is a rule that is called as octant sign. Then we have to, from looking at the cotton effect, we can then find out the actual configuration. So this has been first, we'll start with the octant sign. So here the coordinate system which is chosen for a octant sign is actually, which it is a right-handed one. So the complex, if it is kept in such a way, the central atom is at a 0 point with the ligands and their specific arrangement. So the sign of the product of the coordinate, it gives us the sign of the each octant. So if any chelating ring is there, we can add the octant sign to its constituent atoms. So the optical activity of the complex is not affected, but the static or vibrational induced asymmetry, they are affected. So so we'll start with monodentate ligands. So here in monodentate ligands, we must follow the donor atoms are they are having the positions in the coordinate system which are not similar to that of generally of the xy axis. So for here, let us consider this example mx4, this complex where the ligand here LPN, it indicates L propylene diamine. So according to the first normal conformational analysis, the most stable form it would be have two methyl group, and here in the equatorial position, and thus the chilled ring will be here in figure 15.5b. This is what should be the most appropriate convention. So here the halogens on the nitrogens, they are not shown here, although there are other atoms on nitrogen. So using the octant sign of the complex, we can assign the actual configuration. Figure. So here the figure 15.6b, so here it indicates, here the C2 is live, so here it indicates that there is negative octant sign. So for other bistentate complexes, the octant sign, the use of octant sign has been indicated here. It has been how to provide for various types of complexes. Now here it has been shown. Now we'll discuss the ORD curves, that is optical rotatory dispersion curves. These are of two types. One is the plane curve and another is the anomalous cotton effect curve. So here is the plane curves are of two types. One is the plane positive, where the specific rotation it increases with decreasing wavelength, and the plane negative, where the specific rotation it decreases with decreasing wavelength. Here it has been shown in figure 15.11, the plane curves. Now the anomalous curves or the cotton effect curves, they are obtained for optically active compounds which have chromophores. Chromophores are the molecules that can absorb in the UV region. So they are of two types. One is called as the single cotton effect curve, another is called as the multiple cotton effect curve. Now single cotton effect curve, they show maximum and minimum both occurring in the region of maximum absorption. So here in figure 15.2, it is a positive cotton effect curve, and in 15.12b, it is a negative cotton effect curve. So these are in figure 15.13, we see multiple cotton effect curves having, here it is a positive charge, and in figure B, it is a negative charge. Now, assignment of configuration using ORD. So the ORD, it has been used to assign configuration based on looking at the curves that we have obtained. Even though here these are the curves that has been obtained, nowadays this process is not followed, and much of the process it focuses on circular dichroism. It is a very simple instrument, and the differential absorption of the, it focuses on the absorption of the light towards left and right, circularly polarized right. So now we know that this is the major working of a figure 15.5. It shows the working of a CD, that is circular dichroism. And here the circular dichroism curves, that has been right-handed and left-handed polarized curves, and they have, that has been shown here. So now we can measure CD with the help of a normal spectrophotometer. Here in 15.17, this spectrum, it is that identical to that of an UV spectrum, except here we know that this is positive. This, when it is, this represents a positive curve and this represents a negative curve. The sign of delta E, it is also the same as the sign of the cotton effect, which indicates the positive deflection and the negative deflection. Now assignment of absolute conformation using CD. So here CD complexes that have the same sign of CD, it will have the same absolute configuration. So first let us consider this example, the absorptions and CD spectra. Here it is shown in figure 8, particularly for this complex. So here the CD isomer, it gives positive deflection, and the delta minus, it shows the negative deflection. So these observations, they match with the, with that we have seen in the reported data. So then, sir, this is how CD has also been used to identify between assign configuration to facial and meridional isomers. Here an example, here it has been shown. However, what happens here is both, which the facial and meridional isomers, they are use the term for the R notation and their S notation, here as here it is indicated in this figure. Now the facial and meridional isomers, they have different spectroscopic properties, and that is why they differ in their positive and negative sign. Here the absolute configuration of some of the cobalt complexes has been listed in figure 14.3. The When we look into the spectra of facial and meridional isomers, then we'll go for R and S prefixes. So this prefix was proposed by Kahn, Ingold and Prelog notation, and this is based on the priority of assigning the highest priority to the group that contains the highest molecular or atomic weight. So here if we look into figure 12.23, in this configuration, in the RS configuration, if the priority of the group it moves towards right hand side, then in a clockwise manner, then it is called as rectus or R notation. But if the priority it moves of the various groups present in the metal, it moves anti-clockwise, that is the sinister metal, it is called, given the S notation. So this is how we give L and S notation for different enantiomers. Then assignment of ligand conformation using CD. So the here the particularly for in CD here they are represented as delta, which implies right handed, and lambda, which implies left handed. So here, if two in this, when we look into figure A, here it is a right-handed complex, so that is why it is represented as delta, and here it is a left-handed complex, and here this is implies as lambda. So here this is for a simple representation. When we talk of figure 15.25, this is for interaction in square planar complexes where more than one chelated rings are present, and they are called as M lambda lambda, M lambda delta, depending on their stability. Now here in figure 15.26, S and minus notations have been indicated, and 15.27, the delta and lambda conformation they has been represented here. Now enantiomers, here we we have to the configurations and specific rotation of some cobalt complexes with R and S ligands, they have been shown here. And particularly if we here, this is the figure absorption spectra and CD spectra that has been combinedly shown for one ligand, and thus from this ligand we can look from this figure or the spectrum, UV spectrum and CD spectra, we can find out their configuration of this complex. So thus, in comparison to ORD spectra, the CD spectra is it is more widely used for the interpretation of the stereochemistry. Then coming to intervalence spectra. The intervalence spectra, it is caused by electron transfer from one metal to another metal, and it is called as IT, and it is not found in the spectrum of this. So because here this figure, if we look into the figure, it applies to similar to the principles of Frank Condon principle, and that this is how the reaction profile for different intervalent spectra is shown here. For here it is for a symmetrical complex. This spectra, it indicates for an unsymmetrical complex, which where the products are more stable than the reactants. This in the spectra for a unsymmetrical complex, and the products are less stable, and this is for a total ground state spectra, which represents like this. So this is how we represent IT spectra, that is intervalent spectra. The here the alternative energy possibilities for unsymmetrical mixed valence complexes, it has been for shown here. Now molecules for inner precursor complexes may be found in mixed valence complexes. So electronic coupling that occurs between redox site from outer sphere overlap, they lead to example in this. So IT, that is intervalence transfer, does not have favorable overlap, so that occurs in a very low intensity. So these are very unpopular. The IT, that is intervalence transfer, they are very unpopular. However, this phenomena is still occurred in some cases. So with this, the the chapter concerning the electronic spectra and the magnetism and electronic spectra is finished. Thank you for today.